Welcome to This Explainer. Today, we are going to bridge that massive, daunting gap between experimental data science and the rigorous reality of the Microsoft AI 300 standard. So if you've ever wondered what it actually takes to run artificial intelligence out there in the real world, you are in exactly the right place. Because let's face it, when AI breaks in production, it's not just a minor glitch. We're talking massive financial risks, an absolute operational nightmare, and a direct hit to your users' trust. Okay, let's just dive right into it by asking, what is arguably the most critical question in the tech industry today? Why is building a model in a lab so incredibly easy, but running it reliably at scale so painfully hard? I mean, imagine you spent weeks crafting this pristine, perfect predictive model on your high-powered laptop. It processes your super clean dataset without a single hitch. But the very second you expose it to live traffic, thousands of concurrent users throwing messy, unpredictable data at it, it completely crashes. We've seen a huge industry shift away from that old historical approach of just training a model locally, dusting off your hands, and calling it a day. Today, deploying a model is really just the starting line. The true challenge of the MLOps behind production AI is keeping that system available, scalable, cost-efficient, and, most importantly, trustworthy once the real world gets its hands on it.
To solve this deployment crisis, we're going to cover 1. The AI production gap, 2. MLOps versus GenAOps, 3. The inner and outer loops, 4. Architecting for GenAOps, and 5. Observability and continuous evaluation. We're essentially going to use this blueprint to logically progress from the core problem through the operations of both traditional and generative AI, all the way to securing our safety net.
Let's kick things off with Section 1, the AI production gap, crossing the chasm. We really need to understand this exact pain point where those perfect little notebook models break down under pressure. This really brilliantly illustrates the industry's massive shift from that old, retired, localized data science approach to the modern, automated, DevOps-aligned AI 300 standard. Just look at the difference here. Back in the day, a data scientist might manually deploy a model file. Think about the pure, unadulterated anxiety of manual deployments. Desperately hoping you dragged and dropped the right files to the right server at 2 in the morning? Yeah, no thanks. Today, we rely on automated infrastructure as code, using tools like Bicep and the Azure CLI to provision resources securely and, most importantly, consistently. And why is that old, static evaluation so dangerous? Well, because data changes the literal second a model goes live. So we've moved completely away from that static point-in-time check to continuous CI/CD pipelines that actually support stage rollouts and automatic rollbacks in the real world. It is a total paradigm shift from research to rigorous engineering. Moving right along to Section 2, MLOps versus GenAOps, different paradigms. To cross this production chasm, we have to clearly define the two very distinct disciplines of modern AI ops. So the absolutely crucial takeaway here is that MLOps is all about managing custom-built machine learning models, whereas GenAIOps orchestrates applications and agents around unpredictable, pre-trained large language models. Think about it like this. Traditional MLOps asks, okay, is this model accurate based on our historical training data? GenAIOps, on the other hand, has to ask an entirely different set of questions. Things like, is this generated response actually useful? Is it safe? Is it grounded in our actual company data? Or did the AI just totally hallucinate? To put that into perspective, if you build a traditional model to predict customer churn, you just want its accuracy percentage. But if you deploy a generative AI agent to handle live customer support, accuracy isn't going to cut it. That agent needs strict safety guardrails so it doesn't just cheerfully offer an angry customer a $1,000 refund out of thin air. You aren't just managing a static model anymore. You are wrangling prompts, complex architectures, and unpredictable AI agents. This brings us perfectly to Section 3, the inner and outer loops, structured workflows. Let's look at how this builds into a workflow that separates all that experimental chaos from production stability. So the inner loop is where your data scientists can safely experiment and track their performance using MLflow, completely isolated from the live environment. This is their dedicated sandbox. And let's be honest, data science is inherently messy. You're testing hundreds of variables, exploring massive data sets, and constantly trying to clean and pre-process information. In this inner loop, they can run hyperparameter tuning and evaluate countless iterations safely. And MLflow is literally the hero here. It acts as this centralized ledger for tracking those experiments and registering models so absolutely nothing gets lost in the shuffle of tweaking values. It guarantees reproducibility and creates a highly protected space where a failure is just a learning step, far, far away from your actual users. But when it is time for the real world, DevOps engineers trigger the outer loop.
This relies heavily on CI/CD principles to orchestrate this exact automated pipeline. The very moment a data scientist registers a new approved model version, boom, it triggers the outer loop. Using tools like GitHub Actions, we systematically walk through these steps. We train or refine the model, package it securely, register it centrally, deploy it to an active online endpoint for real-time prediction, and instantly, and I mean instantly, start monitoring its performance. This is where automation takes the wheel. By completely automating every single one of these steps, we ensure that moving a model from staging into full-blown production is consistent, secure, and perfectly reproducible every single time.
Which leads us to Section 4, Architecting for GenAOps Generative Workflows. With our pipeline established, we need to tackle the unique architectural challenges of generative AI. Optimizing retrieval augmented generation, or RAG, is an absolute necessity here. It acts as your primary tool to control runaway costs and guarantee that your AI's answers are actually grounded in reality. I like to think of it like an open book test. Instead of forcing the AI to memorize your entire company library by fine-tuning it, which, by the way, takes massive compute power and will completely destroy your budget, RAG just intercepts a user's prompt, retrieves relevant facts from a secure database, and feeds that specific context straight to the AI. The cost difference is night and day. This is exactly how we stop language models from fabricating information. It ensures they're answering based solely on your specific approved documents without breaking the bank. To actually bring this all to life, enterprises are relying on a heavily automated tech stack. We're talking Bicep for infrastructure as code and GitHub Actions to orchestrate the entire generative workflow. You've got Azure Machine Learning handling the heavy lifting of compute, while Microsoft Foundry provides the specialized environment for building, evaluating, and deploying these really complex GenAI apps. And right there in the middle of it all, MLflow continues to be vital. It tracks every prompt iteration, version, and evaluation metric across the entire generative pipeline. Together, this integrated stack takes all those disparate moving pieces and creates a tight, secure, governed perimeter that scales effortlessly.
And finally, we reach Section 5, Observability and Continuous Evaluation, Continuous Monitoring. Because, as we've learned, deploying the model is just the beginning. We absolutely must have a safety net.
What's really cool to see here is how we can seamlessly integrate Azure AI Foundry with Azure Monitor to set up continuous, real-time observability for our endpoints while they're under actual production load. This integration is so crucial. It lets you take highly specific, proactive actions. You can apply strict-term block lists to prevent inappropriate outputs, or properly set up your endpoints to handle massive, unexpected traffic spikes gracefully. Because unlike traditional evaluation, which you might only do periodically in a lab, observability is continuous. It gives you that low-latency telemetry to instantly see if an API is throwing a timeout error, or if you're suddenly hitting throttling limits that are quietly frustrating your users. By setting automated alerts for these specific metrics, you guarantee that if a model starts drifting or hallucinating, your system is going to instantly trigger a response. Think about it. If token usage spikes unpredictably, your costs could skyrocket literally overnight. If data drift occurs, your model's accuracy is going to plummet. But by utilizing distributed tracing and automated action groups, you make sure that the exact moment a safety boundary is crossed, your engineering team is notified. It's basically an automated circuit breaker for your AI. If the AI starts hallucinating wild answers, the circuit breaker trips, the system can instantly trigger a safe rollback to a previous stable version, completely averting a disaster and keeping your systems and your users fully protected. So as you look at your own experimental models and pipelines, ask yourself right now, do you actually have the operations in place to survive the real world? Because building a clever AI in a notebook, that's just a really fun science fair project. True success lies in the MLOps and GenAOps pipelines that keep it running safely, securely, and affordably at scale. Thanks for joining me on this explainer, and I highly encourage you to take a hard look at your own AI deployments and ask yourself that exact question today. See you next time.